Now that we've introduced our root mean square speed, we can talk about molecular effusion and diffusion. And what we can say about these concepts is the following. The dependence of molecular speeds on mass has a few consequences on how these particles escape their container or interact with substances in contact with these particles. And from here we can introduce the definition of diffusion and effusion. Diffusion is defined as the spreading of one substance through a space occupied by one or more other substances. And in this case, think of perfume diffusing from one side of a room to another side of a room. The definition for effusion is the escape of tiny gas molecules through a tiny hole into an evacuated space. And think of the helium molecules inside of a balloon. The balloon has tiny little holes, and after a period of time, all those gas molecules are going to go through the pinhole of a balloon. So we have the definitions of these, and so how can we work these together with the root mean square speed? So in 1846, Thomas Graham discovered the effusion rate of a gas is inversely proportional to the square root of its molar mass. So if we were going to compare two gases, gas 1 and gas 2, we can look at the different rates of effusion. So R1 divided by R2 was shown to be equal to U1 over U2, which is our root mean square speed. If we plug in the values and the equations from the previous video, we can say that R1 over R2 is equal to 3R times T1 divided by the molar mass of 1 to the 1/2 power divided by 3RT2 divided by the molar mass of 2 also to the 1/2 power. So if we kind of rearrange this equation a little bit, we can say that R1 over R2, which is the rate of each of these gases, is going to equal T1 times m2 divided by T2 times m1 all to the 1/2 power. A simplification that we can make here is if we have constant temperature, T1 and T2 are going to be the same amount, so they're going to cancel out. So we can say that at constant temperature, R1 over R2 is going to be the molar mass of 2 divided by the molar mass of 1 all to the 1/2 power. So here are our two relationships that we can take away based on the rate of effusion of a gas. And we're going to be able to utilize these formulas in the next example video.